Well, good morning, Chem 20s. I'm going to talk to you guys today a little bit about what makes an acid a strong acid or a weak acid, what makes a base a strong or a weak base, and also what is a monoprotic or a polyprotic acid and base. So you guys know a fair bit of information here already. You already know some empirical, observable properties of acids and bases. You could list a whole bunch, and they're in your textbook as well. Like acids have a pH below 7, so bases pH above 7. Acids turn blue litmus red, bases turn red litmus blue. Conductivity for both of them. That doesn't distinguish between them. That's a common property to them. But you can come up with quite a bit of empirical or observable, testable properties. So then what is it makes an acid strong or weak? Well, how strong an acid is not the same as its concentration, right? Concentration is how many particles there are in a solution per the amount of the solution, like the solvent. How strong an acid is dependent on how much it reacts with water and how much it ionizes to make hydronium. So the difference then between a strong and a weak acid, we have to go back to our modified Arrhenius theory that reacts with water theory and talk about how much does the acid react with water. So you guys already know your strong acids are the ones that are in the data booklet, and they are above the hydronium. And if you were to test them, some observable properties, their pH would be closer to 0, right? The bottom end of the pH scale, the lower numbers, they have a high conductivity when you dip a conductivity meter in, high concentration of hydronium ions, and they react with metals like zinc and other strong metals to produce hydrogen gas to make bubbles, and they react with carbonate. So if you react it with sodium bicarbonate, you guys know, you've done this as a kid, right? When you take vinegar and some baking soda at home, you get this like giant volcano explosion bubbles, right? Well, that's because the acid reacts with the carbonate. So the strength of the acid, we can measure these things about a strong acid. And the reason why it is strong is because it reacts completely with water. It ionizes and it forms hydronium ions. It reacts more than 99% with water. And just a reminder for you, I'm just going to pull this up for a second here. Just move this out of the way for us here and remind you that we have our acids and bases chart, right? And here is all our strong acids. Everybody who is up above the hydronium is strong acids, and everyone below here is a weak acid. Okay, and so, but why? And that's what we're talking about in this booklet. All of these guys here react with water 100%. It's a complete reaction, 99% or higher, and that is going to produce hydronium ions. Okay, the weak acids do not react as much with water, and because of that, they are weak, right? They don't react as much with water. So properties of a weak acid, the pH is going to be closer to 7, right? Not above 7, right? We know that acids are always a pH less than 7. They have less hydronium ions in solution, and they're less conductive, and they don't react as quickly with metals. They're going to bubble more slowly. So a strong acid, remember that we talk about here is this proton, this hydrogen, and it joins onto the water to make hydronium ions. And this is happening more than 100%. We say that this is a complete reaction, and it completely ionizes, and then we're producing this anion as well. And don't forget your states. These guys are aqueous. Okay, so these strong acids are in your data booklet, but the weak acids are not going to react like that. They will not have a complete reaction with water. And in fact, they react less than 50% with water, very, very tiny percentage. So they react incompletely with water. They only ionize a little bit, and they only make a few hydronium ions. So here's an example. Here's this ionizable hydrogen, this hydrogen from acetic acid. We know this guy is a weak acid. Yeah, So he's going to go and join onto the water, and he makes this protonated molecule we call the hydronium ion, but it's not a complete reaction. It's way less than 50%. And that explains why we see these things like less conductive and the pH closer to 7, right? And so there's a bunch of diagnostic tests. You can do pH meter and conductivity, reaction with metals, all those things, but they're all going to show you that a weak acid does not react nearly as much with water as a strong acid does. So that becomes important when we're doing our calculations for hydronium, right? That's why we've never done a calculation of a weak acid. We can't. The concentration of a strong acid, like hydrochloric acid, the acid concentration will be the same as the hydronium because it's a 100% reaction. The hydrogen is going to join on to the water to make 100% hydronium, right? This is a complete reaction. So whatever the concentration that we know of, if I know the concentration of the acid, then that's also the concentration of the hydronium. That's not going to be true for a weak acid because it doesn't react 100%. It only partially ionizes. So if you're asked for a pH of a solution, it's always going to be a strong acid until we get to Chem 30, and then you'll learn how to do something different. So the pH, we just write out our formula, negative log of hydronium. Well, we know the hydrochloric acid is a strong acid, so we also know the hydronium ion concentration. So it's 0.15 moles per liter. This has 2 sig digs. Up front doesn't count. This guy counts, this guy counts. So that means 2 after the decimal is our sig digs. Okay, so strong acids, we can use them directly because they ionize 100%. If you know the strong acid concentration, you know the hydronium ion concentration. So the difference being on a weak acid that it doesn't ionize as much. So if you were asked, if you had the exact same concentration, you had an acetic acid and you had a hydrochloric acid, you would not get as much ionization in the acetic acid because it's weak. It doesn't produce as many hydronium ions. The pH won't be as low. The pH is going to be closer to 7. So maybe it's 4 or 5 or something, but it's certainly not 7. So what about bases? Are there strong and weak bases? Absolutely. If you have hydroxide, that's a strong base. So sodium hydroxide, lithium hydroxide, anyone with hydroxide is going to have high conductivity, high pH, right? Up towards the closer to 14 at the end of the pH scale. And they're going to 100% dissociate. They're going to make hydroxide ions in solution. A weak base like ammonia is not going to do that. It's not going to react as much with water to make hydroxide. It won't have as high of conductivity and it won't have as high of pH. So notice that all the strong bases have to have hydroxide in the formula. What do? They don't need to react with water. They just dissociate. They just break up into their ions, and that's a complete reaction, 100%. Okay, so when you are looking at a formula, all of your strong bases have hydroxides in them, right? They have the OH in the formula. They dissociate completely. They make hydroxide ions in solution. So all of your strong bases have M, that's a metal, right? So a metal ion or ammonium ion, right? So maybe it's calcium, maybe it's strontium, whatever, but it's a metal plus the hydroxide ion, and it just is going to greater than 99% just go ahead and break up into its ions. It is going to dissociate. Weak bases are going to have a pH above 7. That's what a base is, right? But they don't have hydroxide ions in their formula. Instead, think back again to your modified Arrhenius. They have to react with water. So they're forming hydroxide ions, absolutely, but they're only reacting partially, less than 50% with water. So less than 50% reaction going on here. So they do not have the OH in the formula, right? So an example is ammonia, right? You guys should know that from Science 10. Ammonia is, even though it's molecular, it's actually a base. So it has to react with water to produce hydroxide ions. Okay, so reminder of our pH scale, that pH and pOH, they add up together to make 14. And so our pH Closer to zero is our stronger acids. And as we go closer to 7, we know 7 is neutral. Our weak acids are going to be closer to 7. Our weak bases are closer to 7. And our strong bases are up at the higher end here. So the pOH is the exact opposite. So a strong acid is going to have a pOH closer to 14. And a strong base is going to have a pOH closer to 0. Okay, so again, how do I know? By looking at a formula? Well, by looking at a formula, I'm looking for, does it have the OH in the formula? If it does, yeah, then we got ourselves a strong base. If not, then we know it's a weak base. And so again, thinking back to modified Arrhenius, how much does it react with water? How much hydroxide ions? If it's got hydroxide in the formula, then you're just dissociating it. It's reacting 100%. If it's a weak base, then you got to react it, and it is not reacting much with water, and you don't get very many hydroxide ions. Okay, so last concept here, monoprotic acids and bases. And this is going to have to be video number 2. I'm getting close to my time here, so I will come back with just a short video on monoprotic acids and bases. All right, that's it for this video. I'll have a second one out in just a bit. Take care.